Welcome to AI Frontiers, where we explore the cutting-edge research shaping tomorrow's artificial intelligence. Today, we're diving into 18 groundbreaking papers from computer science learning research that were published on September 23, 2025. These discoveries challenge fundamental assumptions about how machines learn and think, revealing breakthroughs that could reshape the entire field of artificial intelligence. Picture this. While you were sleeping last night, 18 research papers were published that could fundamentally change how machines learn, think, and solve problems. One of these papers just proved that a training method we've relied on for 40 years might not be the best we can do. Another showed that machines can now learn scientific truths that humans literally cannot observe through traditional methods. And perhaps most surprisingly, researchers discovered that making AI reason longer doesn't actually make it smarter. In fact, it might make it worse. These aren't just academic exercises, they're the blueprints for the AI systems that will power our future, from the phones in our pockets to the robots exploring Mars. What makes today's collection particularly fascinating is how it captures machine learning at a pivotal moment. We're seeing researchers challenge fundamental assumptions, propose radical new approaches, and achieve breakthroughs that seemed impossible just months ago. Each paper represents hundreds of hours of brilliant minds pushing against the boundaries of what we thought machines could learn and do. Computer science learning sits at this remarkable intersection, where theoretical advances meet practical applications, creating an environment where breakthrough insights can emerge from unexpected connections. To understand the significance of today's research, imagine machine learning as a vast ecosystem, like a digital rainforest, where different species of algorithms evolve, compete, and collaborate. Computer science learning, or CSG, is the study of this ecosystem itself, how these algorithmic species develop, what makes them thrive, and how they adapt to new challenges. This field sits at the intersection of mathematics, computer science, and cognitive science, much like how a rainforest exists, where land, water, and air meet. Just as different species fill ecological niches, machine learning algorithms specialize in different types of problems. The health of this ecosystem depends on diversity, innovation, and constant evolution of new approaches to tackle emerging challenges. Analyzing today's 18 papers reveals 6 major themes reshaping the machine learning landscape. The first theme is the quest for energy-efficient and sustainable AI. Think of this as the ecosystem's response to resource scarcity. Traditional neural network training consumes enormous amounts of energy. Imagine running a small city just to teach a computer to recognize cats in photos. Researchers are now developing alternatives that work more like efficient predators, achieving the same results while consuming far fewer resources. One paper shows how alternative training methods can reduce energy consumption by 41%, while actually improving performance, challenging the assumption that more computation always means better results. The second theme centers on making AI systems more robust and secure. Picture this as developing the immune system of our digital ecosystem. As AI becomes more prevalent in critical applications like medical diagnosis and autonomous vehicles, researchers are working to protect these systems from attacks and ensure they remain reliable when faced with unexpected situations. Some papers explore how attackers might exploit AI systems using sophisticated deception techniques, while others develop new defenses to maintain system integrity. This work is crucial as we deploy AI in increasingly sensitive and high-stakes environments. The third theme involves privacy-preserving machine learning. This is like developing camouflage and protective behaviors in nature, finding ways for AI systems to learn and share knowledge without exposing sensitive information. Researchers are creating methods that allow hospitals to collaborate on medical AI without sharing patient data, or enable companies to improve fraud detection while protecting customer privacy. It's a delicate balance between utility and protection, requiring sophisticated cryptographic techniques and careful protocol design to ensure both learning effectiveness and privacy preservation. Among the many remarkable discoveries in today's collection, several findings stand out as potential game changers for the field. Perhaps the most surprising discovery comes from research on how AI systems reason through complex problems. For years, researchers assumed that longer, more detailed reasoning would lead to better performance. like believing that showing more work on a math test always improves your grade. But new research reveals this intuition is fundamentally wrong. The quality of reasoning steps matters far more than quantity, and systems that generate shorter, more focused reasoning often outperform those that produce lengthy explanations. Another breakthrough challenges one of the oldest assumptions in machine learning by developing alternatives to backpropagation that not only match its performance, but exceed it while using significantly less energy. For our paper of the day, let's dive deep into one of the most groundbreaking pieces of research in this collection: Beyond Propagation, Alternatives for Neural Network Training by Spyra. This work represents a fundamental challenge to one of machine learning's most sacred assumptions, and could reshape how we think about training artificial neural networks. To understand why this research is so significant, we need to appreciate the central role that backpropagation has played in machine learning for over 4 decades. Backpropagation has been so successful and ubiquitous that most researchers simply accept it as the natural way to train neural networks. But Spyra's research tells a different story, investigating 3 alternative training methods: forward-forward, cascaded forward, and mono-forward algorithms. The experimental methodology in Spyra's work demonstrates exceptional attention to detail. Each algorithm was implemented on its most suitable architecture: multi-layer perceptrons for forward-forward and mono-forward, and convolutional networks for cascaded forward. The researchers used automated hyperparameter optimization to ensure fair comparisons, and they measured not just accuracy, but also energy consumption and training time using specialized hardware monitoring tools. The results are nothing short of revolutionary. The mono-forward algorithm doesn't just compete with backpropagation, it consistently outperforms it on classification tasks, while using 41% less energy and requiring 34% less training time. These aren't marginal improvements, they represent a fundamental shift in the efficiency-performance trade-off that has constrained machine learning development. The implications of Spyra's work extend far beyond academic interest. As AI systems become larger and more energy-intensive, finding training methods that maintain performance while reducing computational requirements becomes critical for sustainable development. The clear environmental benefits demonstrated by this work, measurable reductions in carbon footprint alongside performance improvements, provide a concrete path toward more responsible AI research. The work also opens new research directions that could reshape neural network design. If local learning rules can outperform global optimization, what other assumptions about neural network training might be ripe for reconsideration? The research provides a rigorous framework for evaluating alternative training methods and establishes benchmarks for future work in this area. Looking toward the future, the landscape of machine learning research appears to be entering a period of fundamental transformation. Think of the field as standing at the edge of a vast frontier, with multiple paths leading into unexplored territory. One path leads toward more sustainable and efficient AI systems that achieve better results with less computational overhead. Another path explores the integration of different types of AI systems into more capable and flexible architectures through modular approaches. A third path focuses on incorporating human knowledge and physical principles directly into learning systems, dramatically reducing training data requirements. The theoretical foundations of machine learning are also experiencing rapid development, moving toward rigorous mathematical frameworks that can predict when and why certain methods will succeed. Today's journey through the latest machine learning research reveals a field in remarkable transition, where fundamental assumptions are being challenged, new theoretical foundations are being established, and practical applications are reaching unprecedented sophistication. From energy-efficient training algorithms that outperform decades-old standards to AI systems that can learn scientific truths from synthetic data, we're witnessing breakthroughs that could reshape how machines learn and think. The 18 papers we've explored represent more than just academic achievements. They're blueprints for the AI systems that will power our future. What strikes me most about this collection is how it balances ambition with rigor, pushing the boundaries of what's possible while maintaining careful methodology that ensures these advances are reliable and reproducible. This analysis was created using AI synthesis, powered by Claude Sonnet, with text-to-speech synthesis by Deepgram and image generation through OpenAI tools. Human expert review was conducted on all synthesized content to ensure accuracy and clarity. While every effort has been made to accurately represent the research findings, potential oversights may exist, and readers are encouraged to consult the original papers and references for complete technical details. The synthesis process involved careful extraction of key findings, methodological approaches, and implications, while maintaining the technical rigor of the original research. I encourage you to explore these papers yourself, dive into the technical details that fascinate you, and consider how these advances might impact your own work or interests. Share your thoughts with the research community, engage with the authors, and perhaps most importantly, stay curious about what tomorrow's research might reveal. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.